Hi, good people. I'm going to start making some of these videos to review some of the factoring that we've learned and also to move forward with this unit and get into some new stuff. Really miss you guys. Hope you're all doing well. And I'm going to close my camera app now, so the rest of this is just going to be you looking at my screen and me doing some problems. But hopefully this will work very similar to what we did in class. Let's get started with a review problem, factoring by grouping. Okay, so we have a 4-term polynomial that has no common factor shared by each of the 4 terms. If you look at the first 3 terms, they all have an x that we can factor out. If you look at this term and this term, they're each divisible by 2. These are each divisible by 7, but if you look at the whole thing all the way across, there's nothing that evenly divides every single term. So the thing is, it has no greatest common factor that we can factor out other than 1. So what we do is we kind of group it together. We focus on the first 2 terms and the last 2 terms separately. If you look at the first 2 terms, they have a greatest common factor of 2x. And you could use the greatest common divisor function of a TI-84 to figure out that, but the biggest number that divides 6 and 4 is 2. So we're going to factor out 2x because they each share an x in common too. So 2x multiplied by what would equal 6x squared? Well, that would be 3x. 2x multiplied by what would equal 4x? That would be 2. Now let's look at the last 2 terms of this polynomial, 21x plus 14. Each of those terms is evenly divisible by 7, so I'm going to factor out a 7. 7 times what would be 21x? 3x. 7 multiplied by what would be 14? 3. Oh, sorry, 2. Okay, now we notice that we have this common binomial factor that exists at these 2 spots in this expression. We can factor out that common binomial factor just as we would factor out anything else. So I'm going to factor out that 3x plus 2. When I factored out the 3x plus 2 from here, I was left with a 2x. When I factored out the 3x plus 2 from here, I was left with a plus 7. And now we are factored. So we took that original 4-term polynomial and we changed it into the product of 2 binomials, which is very useful. We use that to solve a lot of quadratic equations, and I'll be showing how that's used in the next video that I upload. Let's do another example. Oh, by the way, if you want to use the calculator I'm using here, you can actually download it from Texas Instruments website right here. I'm going to put the link here in the description of the video, so you can just click on it. That will work on a Windows or a Mac. If you don't have a Windows or a Mac computer, you could use the wabbitemu app on your Android device, or you could use the Taculator app on your iPhone. You would find that just by going to the Apple Store. Alright, let's do another example. This is a try problem, so if you want, you can pause the video now and try it on your own. And I'm going to show you the solution. So we have the original polynomial 5x squared plus 55x plus 3x plus 33. Again, just as in the last example, there is no number that can be factored out of all 4 of these terms other than the number 1. So we isolate the first 2 terms and the last 2 terms, and we look at them separately. We look at the first 2 terms, 5x squared plus 55x. They're each divisible by the number 5, and can we factor anything else out? Yes, they each share an x. We can't factor out any more x's than are actually there. So I said this a little differently last time. This time I'm actually going to go through the real process. You take the 5x squared, the first term, and you divide it by the GCD. 5x squared divided by 5x is just x. That's what goes here. You take the second term, 55x, and you divide it by the GCD, 5x, and that equals 11. That's what goes here. All right. Now this last 2 terms in the expression, these have a greatest common factor of what? Well, what's the number that goes into both 3 and 33 evenly? It's 3. We're going to factor out a 3. And what is 3x divided by 3? It equals 1x. What is 33 divided by 3? That is 11. Alright, so notice that we have a common binomial factor right here, that x plus 11. We can factor that out. And when I factor out the x plus 11 from the first part of this expression, I'm left with a 5x. And when I factor out the x plus 11 from the second part of the expression, I'm left with 1x. And that's our answer. If you wanted to check your work, you can multiply that binomial times that other binomial by foiling it, or using the distributive property, and you would find that you would end up with something like this. Alright, now for the real deal, you ready? These were sort of already set up for you. This is the real use of using the grouping method to factor polynomials. We like to use the grouping method when we're factoring quadratic trinomials that have a leading coefficient other than 1. This normally would be kind of difficult for people to factor. Many teachers will tell their students just to guess and check and think about the binomial that you can multiply to equal this. Now there's a lot of things that multiply to 12. 1 times 12, 12 times 1, 2 times 6, 6 times 2, 3 times 4, and 4 times 3. You can get lucky and get it on your first try, or it might take you 3 or 4 tries to come up with the correct answer. There is a way to do it without guessing at all, and that's called the grouping method, which I'm about to teach you right now. So this is a little bit new. You want to begin by taking the leading coefficient and the constant at the end and multiplying them together. So what are these equal when we multiply them? These equal 5 times 12 is 60. And then you're looking for something that adds up to the number in the middle. So we're looking for two numbers that multiply to 60 and add up to 19. And if you're not good at factoring numbers, what I suggest you do is you just take the number that you're factoring and divide it by 1, then divide it by 2, then divide it by 3. And you don't have to go all the way up to the whole number. There's a rule in number theory that says if you check up to the square root of that number, you will have ran into all of the possible factors of that number. So the square root of 60 is 7 point something, so we only have to check up to 7. Okay? So I'm going to write out all these factors. 1 multiplied by 60 is equal to 60. 2 multiplied by 30 is equal to 60. 3 multiplied by 20 is equal to 60. Does 4 go in this 60 evenly? Yes, it does. Oh, sorry. 60 divided by 4 is 15, so we have 4 times 15. Remember, we're looking for the pair of numbers that adds up to 19. Do any of these add up to 19? Oh yeah. 4 and 15. So, we found our pair. So what we actually use those two numbers, is to split up this middle term, this 19n. We split it up as 4n plus 15n. The order in which you write those doesn't matter. I could have written 15n plus 4n, but since I haven't written 4 and 15 here, I'm just going to stick to that order. 5n squared plus 4n plus 15n plus 12. Now we have a factoring by grouping problem similar to what we did on those other slides. So we're going to look at the first two terms, see if there's a greatest common factor that we could factor out. 5 and 4 aren't divisible by anything other than 1, but these each have an n in common that we can factor out. So I'm going to factor out 1n. n times what is 5n squared? 5n. n multiplied by what is 4n? 4. What goes into 15n and 12? Well, they're each divisible by the number Remember, if you're not good at this, you can just use this calculator. Math over 9 will give you the GCD. They're each divisible by 3, so I'm going to factor out a 3. 3 times what is 15n? Well, 3 times 5n. 3 times what number is 12? 4. Notice we have this situation where we have a common binomial factor here that we can factor out further. And we're going to pull out that 5n plus 4. When I factor out the 5n plus 4 from this first part of the expression, I'm left with an n. When I factor out the 5n plus 4 from the second part, I'm left with a 3. Done. That's our answer. So if you want to check your work, you could actually FOIL this answer and verify that it does equal this original problem. I'm not going to do that here. Another example. Alright, so again, we begin this method. Our goal is to factor this as a product of two binomials. We begin by multiplying the leading coefficient and the constant at the end. These have a product of 10, and we have this number in the middle. That's the number that we want our thing to add up to. So we're looking for a pair of numbers that have a product of 10 and a sum of 11. So you could start with your number 10, divide it by the first natural number that you think of, which is 1. So 10 times 1 is equal to 10. Does that add up to 11? Yes, it is. That's the factor pair we were looking for. The only other pair of numbers that multiply to 10 is 2 and 5, and they add up to 7. So we found our pair of numbers that we were after. We use that pair of numbers to split up this middle term. So we have 2v squared plus 1v plus 10v plus 5. And all I did was I expanded this polynomial by splitting this middle 11v as 1v plus 10v. I didn't really change anything. Alright, we're going to group the first two terms and look at them separately. So 2v squared plus 1v, they each have a v, at least, that we can factor out. So I'm going to factor out 1v. And v times what is 2v squared? V times 2v. V times what is itself? V times 1. Over here, what number goes into 10 and 5 evenly? The answer is 5. 5 goes into 10v how many times? 2v times, because 5 times 2v is 10v. 5 goes into 5 how many times? 1 time. Notice that we have this common binomial factor of 2v plus 1 that exists both here and here. And we're going to go ahead and factor that out. 2v plus 1, when factored out of the first part, we're left with a v. When you factor it out of the second part, we're left with a 5. That's our answer. If you wanted to verify that that is the correct answer, you could go ahead and FOIL it. 2v times v is 2v squared. 2v times 5 is 10v. 1 times v. 1 times 5. Take the middle two terms, combine like terms, you get 11v, which is what we have up here. So we checked our work. We're good. Alright, another example. Alright, so begin by multiplying the leading coefficient by the constant at the end. These two numbers have a product equal to 4. So we're looking for a pair of numbers that have a product of 4 and a sum of 5. What are two numbers that go in the 4? 1 goes in the 4 times. 2 goes in the 4 2 times. Do either of these pairs add up to 5? Oh yeah, this one. So we're going to use the 1 and 4 to split up that 5. We're going to split up 5n as 1n and 4n. We have 2n squared plus 1n plus 4n plus 2. This is something where we're going to focus on the first two terms, factor out the GCF. The greatest common factor of 2n squared and 1n is just n. try to not lean on my board here. N multiplied by what is 2n squared? 2n. N multiplied by what is 1n? 1. What's the greatest common divisor of 4n and 2? 2. 2 evenly divides both of those. 2 times what is 4n? 2 times 2n. 2 times what number is itself? 1. These are each evenly divisible, they have a common binomial factor of 2n plus 1 that we can factor out. So we're going to pull out that common factor, and we're left with n plus 2. Done. So our goal in these problems is to take the original quadratic trinomial and to change it into a product of two binomials. Again, this is very useful. We use this to solve a lot of quadratic equations, a lot of physics problems. I'm going to show you a few examples of that in the next video that I upload, how it's actually used in the real world. Here's a try problem for you. So if you want to try this on your own, go ahead, pause the video now. I'll be solving it so you check your work. So you want to begin by taking the leading coefficient and the constant at the end, multiplying them together. Ooh, this is going to be a big one. These two numbers multiply to 196. So we're looking for a pair of numbers that have a product of 196 and a sum equal to 53. I don't know what those two numbers are off the top of my head, so just so you're not scared, you don't have to divide 196 by every single number from 1 up to 196. There's a rule in number theory that says you only have to check up to the square root of that number. So we only have to check up to 14 to find the correct pair of numbers that evenly factor 196 and add up to 53. So I'm just going to go through this using like the brute force method by actually dividing 196 by 1 all the way up to 14. And I'm going to write out every factor pair. Then we're going to look among our factor pairs for the pair of numbers that adds up to 53. 196 divided by 1 is 196. 196 divided by 2, 196 divided by 2 is 98. 196 divided by 3 does not go into it evenly. 196 divided by 4. Alright, so we have 2 times 98 is 196. 4 multiplied by 49 5 doesn't go into it evenly. 6 doesn't go into it evenly. 7 goes into it 28 times. 196 divided by 8 doesn't go into it evenly. 196 divided by 9 doesn't go into it evenly. 196 divided by 10 doesn't go into it evenly. 196 divided by 11, nope. 196 divided by 12, nope. 196 divided by 13, no. 196 divided by 14 is 14. So we have our factor pairs all written out. Do any of these pair of numbers add up to 53? Did you find it? Here it is. This pair. So we found a pair of numbers that multiply to 196 and add up to 53. We're going to use that pair of numbers to split up this middle term as 4a plus 49a. So we have 7a squared plus 4a plus 49a plus 28. And now we're going to focus on our first two terms. These have an a that we can factor out. A times what is 7a squared? 7a. A times what is 4a? 4. These two have what number that we can factor out? 7. They're each divisible by 7. 7 times what number is 49a? 7a. 7 times what is 28? 4. So notice that we have this common binomial factor here of 7a plus 4. We can factor that out of each of the first and second part of this expression. 7a plus 4 gets factored out, and we're left with that a. 7a plus 4 gets factored out, and we're left with that 7. Done. So we found a binomial times another binomial that equals this quadratic trinomial. That's what we were after. Alright, so this is the end of this video. At the next video that I'm going to upload is going to have a few ways that you can actually use this method to solve some physics problems. We're going to revisit one of the earlier constructor responses that we did this year that we used a calculator to solve, and now we're going to actually solve it by hand. And I really miss all you guys. Thank you for watching, and I look forward to getting into some new stuff with you. None of this is graded yet, but in the future I will probably have some questions that are attached to these videos, and feel free to reach out to me via email or Google Classroom. I look forward to seeing you guys again soon.